Two points are wandering. One is trapped inside a circle. The other is trapped inside a square. Nothing else connects them. Watch only the point exactly halfway between, their midpoint. It fills in this. A square with the corners rounded off. Where did the round corners come from? Neither shape has a curve in that place. And how much area is this exactly? Here is the whole trick, and it is one sentence. When two things move at once, stop one of them. Move the other alone and see the shape it draws. Then let the first one go and drag that shape along with it. The reason this is allowed sits in the plus sign. A plus B does not mean two things happening at the same instant. It means travel A and then from wherever you landed, travel B. Once you read the plus that way, the picture builds itself in order. Start with the easiest case. One thing moves, the other is a single point. Take a shape and add a fixed arrow to every point in it. Every point travels the same distance in the same direction, so the shape does not stretch or turn. It simply slides. A shape plus a point is that shape shifted. This is the atom of everything that follows. Hold on to it. Now let both move. One point runs over the blue shape, the other over the orange shape, and we take every possible sum. Freeze the orange point first. What we get is the blue shape, shifted to sit on that orange point. We just proved that. Now release the orange point. Its shifted copy of the blue shape travels with it, and the copies pile up. The answer is everything those copies cover. Not a formula, a sweep. Glue the blue shape to the tip of the orange arrow and drag it over the whole orange region. What it paints is the set of all sums. Three examples from small to large. Take a straight line through the origin and add a short arrow that is allowed to grow from nothing up to its full length. Stop the arrow at 0, and we have the bare line. Now let the arrow grow. The line slides sideways, and its copies stack against each other with no gaps. What they fill is a band, the region caught between the original line and one parallel copy of it. A one-dimensional thing plus a one-dimensional thing, and we got area. That is the sweep doing the work. Now two circles, both free to point anywhere. The first arrow has length 2, and its tip runs around a circle of radius 2. The second has length 1. Freeze the long arrow. The short one adds a small circle of radius 1, drawn around the tip. Release the long arrow, and that small circle rides around the big one. The band it paints is a ring. The closest the sum can ever get to the center is 2 minus 1, which is 1. The furthest is 2 plus 1, which is 3. So the answer is everything between radius 1 and radius 3, and its area is 9 pi minus pi, that is 8 pi. Now we can answer the question we started with. The circle has radius 2. The square has side 2. We want the midpoint of a point in each. The midpoint is 1/2 of the first, plus 1/2 of the second. So shrink both by 1/2 before you start. A disk of radius 1 and a square of side 1. Now sweep. Glue the disk to the square and drag it over the whole square. The disk center covers the square. Along each of the 4 edges, the disc hangs over by exactly 1. And at each corner it swings around, tracing a quarter turn. There are the round corners. They are the disc, remembering that it is round at the only places where the square stops telling it where to go. Now count the area, and count it in pieces you can point at. In the middle, the square itself, area 1. Along each of the 4 edges, a rectangle 1 by 1, 4 more. At the 4 corners, 4 quarter discs of radius 1. Slide them together and they form one whole disc, area pi. 1 plus 4 plus pi. 5 plus pi. About 8.14. Nothing here was integrated. We only had to know what the sweep was made of. Does it still work when there are 3 of them? Or 4? Three small triangles sit apart on the plane, all the same size, all the same way up. Pick a point on the edge of each, and take the center of mass of the 3. Measure each point from the center of its own triangle. The center of mass is a fixed offset, plus 1/3 of the sum of those 3 arrows. So sweep the sum. 1 arrow traces a triangle of side 1. Add the second, and the triangle it sweeps out has side 2, filled in solid. Add the third, and it grows to side 3. Divide by 3, and we are back to side 1. The area is √3/4. 3 moving points, and the answer is the size we started with. Last one, and this one is genuinely 3-dimensional, so we will look at it that way. 4 numbers, each free between 0 and 1. Build the point, a plus D, B plus D, C plus D. Freeze D. Then a B and C fill a unit cube. Now release D. The whole cube slides along the diagonal direction, 1 step in every axis at once, and it sweeps out a longer solid. The volume is the cube itself, 1 plus the 3 faces that sweep as it travels, each one carving a slanted box of volume 1. 1 plus 3, the volume is 4. This sweep has a name. It is the Minkowski sum, and it turns up wherever 2 freedoms combine. A robot arm that must not hit a wall, the tolerance around a machined part, the blur of a lens. The area of a shape swept by a disk of radius r is always the area, plus the perimeter times r, plus pi r squared. Look back at 5 plus pi. 1 plus 4 times 1 plus pi. It was that formula all along. But there is a real limit, and it is worth saying plainly. The 2 movers must be independent. If the same letter appears in both, they are not free, and the sweep is a lie. Take the point a plus b in one coordinate, and a plus b again in the other. It does not fill a square. It collapses onto a single line segment. Independence is what buys you the sweep. So when several things move at once, do not watch them all. Stop everything but one. Draw what that one makes. Then let the next one go, and drag the picture with it. The round corners were never mysterious. They are a circle, sliding around a corner, doing the only thing a circle knows how to do. Move one thing at a time, and the crowd becomes a shape.